Okay, so thank you very much. So I will present in this talk the programming model PyCOMPSs, which is a task-based programming model for distributed computing, and how we've been extending it for the requirements of the ExaQUte applications. So the overview of the talk is the following. I will start with an overview of PyCOMPSs, and I will mainly describe the basic functionality and the features that were already there that benefit the requirements of ExaQUte, and also a bit of the outline of the runtime. And then I will present what we have been working on in the ExaQUte project to extend PyCOMPSs. And finally, although maybe this is a bit redundant with some of the presentations, but how we have been applying to the multi-level Monte Carlo for uncertainty quantification. So what is the idea, the ambition that we have with the programming model? What we observe is that the infrastructures, the computing infrastructures are every time more complex, with a larger number of devices and very heterogeneous. No? We have heterogeneity inside the node with different type of devices, but also if you look into a larger computing infrastructure, that people is speaking now about the continuum computing, no? That you have devices in the edge, sensors, instruments, Raspberries, whatever, devices in the fog, and then the large computing infrastructures. So here even you have more heterogeneity, no? But on the other side, also the applications, or in general workflows, no, every time are more complex, no, because the user also sees that has more computing infrastructure where to execute the application. So every time they have like more ideas of how to compose different parts of the applications to build larger workflows. No? And a bit our goal here is how to describe these workflows, no, for such environments, how we can help the application developer, the workflow developer, to make their life easier, and following an approach where both data aspects and computing aspects are integrated in a single workflow using high-level and easy-to-use interfaces. No? And what is more, we are looking into how to integrate computational workloads with machine learning and data analytics, and everything powered by an intelligent runtime that can make scheduling and allocation decisions and make also decisions on where to place the data and when to do the data transfers, trying to reduce data transfers to favor locality. Okay. So with this, we've been working on the PyCOMPSs programming model for some years now. The basic ideas is the same of the task-based programming models, where you write sequential code, but you execute in parallel. Okay? And we are based on general-purpose programming languages like Python, Java, C, because we think that are the languages that are commonly used. But we add to this programming that we program in sequential, we add annotations, hints, that are used by the runtime to be able to identify which parts of the application can run in parallel. No? For this, we identify the tasks with the annotations, no? What are these parts that we will write to run in parallel between them, and the directionality of the data. And the directionality of the data means if a parameter is read or written, and with this, we are able to build data dependencies between tasks of an application. No? If a task is generating an output that is needed by another task, then we need to add a dependency here, because the second task cannot start before the first one has finished. So at runtime, we built a task graph that expresses the potential concurrency of the application. No? So in some cases, we can have sequentialities, like here at the beginning, this task cannot run in parallel, but then here in this task graph, we have a lot of these green tasks, for example, that can run in parallel, and later other tasks that can run in parallel. No? An important concept here is also the concept of asynchronicity, no? Because after all these green tasks, we are not synchronizing and then opening again parallel to execute the red task. No? As soon as one of these green tasks finishes, another red task can start because its dependencies has been fulfilled. Okay? So the decision to which task execute depends on the tasks that are remaining to be scheduled and have no dependencies with others, and also on the resources. No? Depending on the number of computational resources that we have, we will run more or less tasks at a time. No? And it also offers the illusion that there is a single shared memory and storage space. No? The idea is that the programmer can write the application as it was going to run in a single node, accessing the local memory and the local disk. And at execution time, the runtime is able to distribute this data in the different nodes of the computing infrastructure, both for memory and for the file system. Okay, so this is very powerful because it enables you to address problems that tackle larger data sets. Okay, so big data applications in general. Okay. And we try to keep this programming model agnostic of the actual infrastructure. No? In this sense, we try to avoid the details about the computing infrastructure in the application. These are kind of hidden in external XML files, whatever, so the user don't need to think if it's executing in an HPC system or in a cloud. The same application, in principle, of course, it depends on the granularity, will perform better or worse, but can be run on large clusters, in clouds, or also we are working now in this technology of the containers, which has become very popular and it's requested by many developers, many communities. Okay. A bit of the syntax. Okay, we are based on Python decorators in the case of PyCOMPSs, which is the binding for Python. Okay, and with this, the main decorator is that task decorator that identifies a method that will become a task at execution time, no? A task that will be a node in this task graph. Okay, and also we need to add the data dependencies. If we don't say anything, it's by default an input. And then we need to identify those parameters that are outputs or inouts. That is when you read and write the value at the same time. No? And besides the task decorator, there is a small API for synchronization that we tried that it's not needed. In this case, for example, we are using it for measuring time. So you need to know when all tasks have finished in order to measure the time if you want to measure the time that takes this piece of code. In some cases, we need to synchronize if we want data that has been generated in a remote node, and we need to bring it to the main node where the master code, where the orchestration code is run. Okay. But we have other decorators that makes the programming model more powerful. For example, one is the task constraints. No? And as I've been speaking, the computing platform is heterogeneous. So then you can think that different tasks may require different type of resources. And this can be, for example, tasks that requires a large amount of memory, or tasks that requires more than one processor, or even tasks that require a different type of architecture, for example, a GPU. So you can, we have a set of parameters. This is not totally flexible, okay? It's a set of constraints that you can give, but it's extensible. So you can indicate in your application these constraints. And this is used by the runtime to perform the appropriate matchmaking between the task and the actual computing node that can run, computing resource that can run this task, okay? And in addition, you can also have different versions, no? Because imagine a typical example is the CPU and GPU example. You may have the code of a task written in regular, in this case, Python code that can run in a general purpose processor, and maybe you have another version for a GPU, no? That invokes a CUDA code or invokes a CUDA library. And you may want to have the code that can run in both platforms, in platforms that have a GPU and platforms that don't have the GPU. So you can do this with this versioning or polymorphism that we call also, where you have the two versions of the task and you indicate this with this at implement. No? And here you identify with this method myfunc, you identify that this method myfunc other has the same behavior as myfunc and can be used, in this case it's not a GPU, but imagine it's for an embedded architecture. You want to have a version specific for ARM or for the RISC-V, and then you have a general purpose version. No? And the runtime will decide at execution time which of these two versions to run. And other things that are also very useful when we want to build more complex workflows is decorators that help us linking with other programming models. I've already spoke about the possibility of having a multi-core task, no? And in this case, what it requires is that the task internally is parallelized, for example, because it's invoking a multi-threaded library or whatever. But we have also, for example, the possibility of having tasks that are MPI applications. And in this case, they can be involving more than one node, okay? More than one node that runs multiple processes in that node. We can also have tasks that are OMPSs tasks, okay? In this case, OMPSs is for runner for OpenMP, or in general, it can be an external binary, okay? And this then can be, for example, in life science, it's very popular to have pipelines or workflows that invoke different binaries, okay, different external applications that are not provided in source code. So the only way is to provide the link to the binary. Okay, so this can be combined then with the constraints also to fit the resources that this external task requires. Okay. Other things that we've been doing a long time is, for example, the extension of the task annotation to be able to deal with failure management. Okay, imagine you have, in this case, the multi-level Monte Carlo, and that it may be the case, or maybe it's not the case because statistically we have to see if this would be correct or not. But imagine that you don't care if some of the tasks fail, and you don't care that they fail. No, so you can indicate that on failure of that task, you just can ignore that this task has failed. Okay. You can also consider that you want to cancel the successors of the task, because this task can have a chain of tasks that depend on it. So you can say, okay, if this task fails, just cancel its successors, or other policies like retry the task. This is also the default that we had, or just fail. Fail will mean that will fail the whole workflow. No? This would be the conservative approach that we were following before, no? That if a task was failing, we were considering that the whole workflow was failing, and we were finishing the whole application. Okay. And in addition to this, you can also have timeouts for tasks. If in some cases there are applications where the user say, no, if this task is the simulation, if it's taking more than 200 minutes, it means that it's not going to go to have a meaningful result. So just cancel this task. Okay? These are things. Or even more, you would like to be able to interact with dynamically with the behavior of the workflow. And for this, we have added the possibility of raising exceptions from the task. No, this as a method, as a Python method, you can always raise an exception. But the problem was that the runtime was able to catch this exception. And now what we do with this mechanism is this: we are raising an exception. That is a COMPS exception, is a special exception that can be catched by the runtime, okay, and make decisions on what to do with some tasks. For example, if we have a group of tasks and one of these tasks, for example, raise an exception, we can decide to cancel the tasks in the group, and then after this exception, decide to launch other tasks or to perform another behavior. No? So this offers the possibility of doing some dynamic behavior. For example, this could be applied in multi-level Monte Carlo to detect if the convergence has been reached. Okay? And if the convergence have been reached, decide to stop the generation of new batches, new execution of new batches in the next iteration, for example. Okay. Another extension that we did, I think more or less during ExaQUte, is the extension to support collections. Okay, so in this case, it's not that we were not able to support collections. Collections can be a list, can be an array. Okay, it's not that we would not work with them. It's that we were not able to detect dependencies between the subobjects of one of these collections and the whole collection. Okay? Here we have an example. Imagine we have a set of tasks, these blue tasks, that is this perimeter task. In this case, they operate on a single object. Okay? But then in the main program, the results of this individual task is collected into one list. And this is passed as a whole to this other task at all that receives a single list. In this case, is this collection in. Okay? So in this case, this task is able to identify that depends on all these tasks, even there is a single parameter, is able to see that this parameter is composed of objects that come from different tasks. No? The other case, the opposite case, is when we have a task that generates as an output a collection, okay, that the sub-objects of this collection are neat individually on this other task. No? This is an opposite case. We have an operation scale all that operates on the collection, but then we have this other task that computes the area. For this case, a simple examples, no? Computes the area of an object, and it's receiving each of them. Each invocation receives a single object. So being able to identify this type of dependencies, it's important in some applications, like for example, in ExaQUte applications, we had to apply. Okay, then a bit about the PyCOMPS runtime. So the PyCOMPS runtime is executed as a master worker application. So we have a master node that runs the runtime and the main code of the application that is like the orchestrator of the whole application. Okay? The runtime has different components that perform the task analysis, the generation of the task graph. It can be also monitoring the execution. It performs the scheduling decisions when to execute each task and in which resource. It performs also the management of the different resources in the infrastructure and handling the actual task execution and data management. That can be both managing files and objects. So we can have objects from the main program that are transferred to the worker nodes or between worker nodes. Okay? So basically the sequential execution starts in the master node, and as soon as the tasks are generated, they are started to be scheduled and executed in the different resources. Okay? One characteristic that is interesting that I wanted to highlight is the possibility of doing elasticity. And until now, the elasticity, until recently, the elasticity was something considered especially in the cloud environment, where you can allocate more nodes from the cloud provider, and if there was enough workload, add more nodes in order to be able to keep with the requests of the application. No? In this case, we have extended to be able to do elasticity, but in HPC systems. For example, in Slurm managed systems, we can start a workflow application in an initial allocation, let's say 10 nodes. And then if we see that we require more computation, we can request a new node, okay, through a Slurm, and add this node to the actual allocation, okay, building a larger allocation that continues execution. And the same, when we have less workload, we can release these nodes. Okay? This is very common in a lot of applications that have a lot of computation at the beginning, and then at the end has kind of the inverted tree where the workload is reduced. So it's very interesting to be able to release these nodes so other applications can start. Okay, so as I said, some of these extensions were done in parallel also with ExaQUte, but here I will also highlight some of these extensions that were more specific maybe for ExaQUte. No? And one is the support for what we call native MPI tasks. No? Until now, when we were having at MPI tasks, usually were tasks that we already had the binary, okay, like Fortran, typically Fortran MPI applications or CMPI applications, but not Python MPI applications. No? And in this case, we needed this native MPI task, okay, to be able to have the methods in Python, okay, but that are run as an MPI application. So in this case, the MPI tasks run on multiple nodes, the same case as the binary MPI tasks. The input of the task can be a collection, so a set of values that are distributed in the different nodes and the different processes of the MPI application. Okay, and the methods individually, the individual processes may just return a value, an object, but the whole set of tasks will return the task list. Sorry, that's why here we annotate this task as a list, because here it seems it's the code for a single process, but in reality, the whole task is like a set of tasks, that each of them run an MPI process and each of them return a value. So that's then collected by the MPI worker, returning a list. Okay. And the worker, for the worker, instead of having the regular worker that we have, it's a specific worker for MPI that is invoked and runs the MPI task and then is closed. Okay. Other extensions that we did for ExaQUte is in order to be able to support at the same time MPI and OpenMP. This was already somehow there, but we fine-tuned it in order to be able to have a given number of MPI processes, and then inside each MPI process a number of OpenMP threads. Okay, this case, for example, we are having 16 MPI processes, as it's annotated here in that MPI task, and then each of them can have, for example, 48 threads, 48 OpenMP threads. Okay, we changed also the interface. Before this, instead of being process, was called computing nodes, which was a bit less intuitive for MPI developers, so we changed the parameter name to processes. And also before, the number of processes was the product by default, this value by this value, and we make it this other way, where here you have the number of processes, and here in this case, the number of OpenMP threads per MPI process. Another more significant extension was required to be able to do more different mappings of the input data into the processes. In this case, we wanted to be able to define that the list that is the input, in this case, this collection that is the input to this set of MPI processes, that can be distributed between them. So if not, by default, before, the processes will be receiving all the data. And if you think that this is run in a distributed platform in different nodes, this will represent different transfers. Okay, so to avoid these transfers, and especially if the data is not needed, it's important to be able to map the data that is required by each node. In this case, we identify data layout by adding to the name of the parameter this _layout here in the annotation. And we can give the number of blocks that you have here in this data, the length of the block, and the stride that is used to access by each MPI process. Okay, I will show this with an example because I think it will be a bit more clear. Okay, in this case, for example, we have an MPI application that runs with 4 processes, and in each of them is only one thread in this case. And we specify that we have 4 blocks, each of them of length 2 and a stride 2. So basically, this is the structure that we are having. We have 8 elements. Each of them is a block of 2. And since it's a stride 2, we have the 2 first mapped to P0, the 2 next to P1, and so on. Okay, so this then for accessing by each process the first element of its block, it can access directly using the 0 index, okay, or without index. So it's the relative index of the block that is operated by the process. Okay. Another example in the next slide is here, for example, where we have, in this case, 7 processes. Okay, here the block kind, maybe the block count should be 7. Sorry, I think I made a small error here. 7 blocks of length 2, but the stride is now 1. No, in this case, we have also still 8 elements, but now they are grouped in different groupings. Since the stride is 1, we have the 2 first elements that will go to P0, the 2 next elements will go to P1, and so on. Okay, so this would be another option. And the access to element 0, before I was indexing with 0, but you can also directly, this would be the first element of the block for each MPI process. So for P0 would be this element, for P2 would be this other element, would be the data or data 0 element. Okay, then during the project, we have been working with different partners to integrate this PyCOMPs programming model in the application that is solved. No? So for this, we have these workflows that compose multi-level Monte Carlo workflows that invoke MPI solvers, okay, performing multi-physics problems and adaptive mesh refinement. No? So the workflows involve simulations of craters and invocations to the MMG measure through the XMC Monte Carlo library. Okay? And in this case, as you know, applied to the wind engineering and civil engineering. Okay? Some of the things that we've been done in this application is first enable the parallelism between tasks. So we have the workflow is composed of different invocations to different simulations, for example. No? So to be able to perform these simulations in parallel. Okay. Also to enable the parallels inside the task because they are MPI. There can be MPI or OpenMP tasks or a hybrid MPI plus OpenMP. And in addition, we have worked especially with Simne, on enabling the synchronous executions between multiple batches of the multi-level Monte Carlo algorithm. No? So the initial schema is the one that we can see here, where this represents, for example, this set of tasks. The red tasks represent a first batch of tasks, and here some of the reduction tasks. And then we had here a synchronization point that didn't enable this second batch to run in parallel with this first one. No? So this was the problem that we wanted to avoid. We wanted to be able to overlap multiple batches between them. Okay, and this is the case. For example, here the strategy has been to start multiple batches at a time, and then to only have a local synchronization point. So here now the synchronization point is waiting for this batch to finish. And when this batch has finished, can start a new batch that can run in parallel with the others. Okay, and then this point here that before would have gone through a global synchronization point is not affected by this local synchronization point and can run in a synchronous way and enabling this parallelism between batches. Okay, the idea is to be able to use all the computing resources while there is load to be processed. Okay? This has been applied, for example, one of the examples we ran was these experiments on a two-dimensional flow using a square building. Okay, and in this case, this was published in a joint publication that demonstrated excellent scalability using up to 128 nodes with a bit more than 6,000 nodes in Mare Nostrum 4, okay, and running this problem, okay. So a bit the conclusions. Well, we think that we have demonstrated in the project that PyCOMPSs provides a good programming interface that enables this integration of MPI solvers with other computing components, okay, like the RMMG or the multi-level Monte Carlo library. The fact that we use the high-level programming language as interface enables to use the whole expressivity of the programming language, no? Enabling the development of complex algorithms, as it is the case of the multi-level Monte Carlo. And then we have also demonstrated further extensions like the native MPI or the new extensions to the MPI interface. and the data layout, sorry. There is ongoing work. We have seen some problems with allocation of nodes to MPI processes to promote locality. So here we are doing some extension, and also the support to task nesting that is ongoing that will improve the programmability. And for example, for the synchronous execution that I was telling, if we are able to embed the different batches into one larger task, this problem of the parallelism between batches would be even easier to develop from the programmer point of view. And we would be able to enable this parallelism between the multiple batches in a much natural way than the way that we've been developing in the project. Okay. And this is my presentation. Thank you.